Life on Earth could not exist without this wonderful chemical compound, H2O. In a never-ending cycle, water circulates the planet, preserving the lives of its inhabitants over millennia. But climate change is throwing this dependable system out of balance. Add to that a rising demand for water caused by industry, agriculture, and the world's growing population, and we run the risk of running out of this precious resource. But new technologies looking to nature as a role model and prehistoric knowledge gleaned from bygone cultures are helping researchers worldwide come up with new ideas to sustainably protect our drinking water. And this German research vessel heads out to sea to explore freshwater reserves of great magnitude. Every spring, glaciologist Daniele Farinotti and his team make their way up to the Aletsch Glacier in Switzerland. Below the Jungfraujoch research station at an elevation of 3,350 meters, they measure the depth of the snow. The glaciers of the Alps play a vital role in supplying water to millions of people. They feed water into Central Europe's largest river systems, the Danube, the Rhine, the Po, and the Rhone.
Unfortunately, the glacier's condition is none too pleasing. Switzerland's glaciers currently lose some 2% of their mass each year. So in the last 5 years, they've lost 10% of their entire mass. Sadly, the prognosis for the next 100 years is not terribly rosy either. If we don't manage to lower greenhouse gas emissions, if the way things are going continues, then we'll likely see only the last remnants of ice here, where we're currently standing. No more than that.
For more than a century, scientists have been coming to this area to assess the health of the Aletsch Glacier. How has the snow cover changed over this period of time? With the results of these measurements, the researchers can track the changes to the glacier's mass and determine exactly how much of its volume is lost each year. Subsequent forecasts include global climate data. At the University of Oxford, Friederike Otto works with the Environmental Change Institute. Her research focuses on extreme weather events related to climate change.
Because the atmosphere is getting warmer, more water is evaporating, which means more water vapor is entering the atmosphere and then coming out again as rain. So the whole balance between evaporation and precipitation, which existed with relatively stable global temperatures over the centuries, is becoming unstable and being thrown off kilter.
And that poses a great threat to the drinking water supply of all living beings, because the amount of fresh water on Earth is limited. That's because almost all the water on our planet is held in the oceans, so it's salt water, some 96.5%. The amount of fresh water is therefore relatively small, just 3.5%. And most of that is stored as ice or snow in mountainous regions and at the poles. That leaves only a fraction. Just 0.3% of the water on Earth is accessible to humans as drinking water. Currently 22 kilometers in length, the Aletsch Glacier is the biggest glacier in the Alps. Its vast size means short-term weather events are barely noticeable. That makes the glacier a reliable climate indicator, suitable for long-term observation. During their last measurements in 2020, the glaciologists found the amount of snow had reached a record low, the lowest amount since the first measurement was taken in 1918.
Und wie das funktioniert, ist, dass wir im Prinzip zweimal pro
How
Jahr
this all works is we're basically on location twice a year.
am Ende des Winters.
We come once at the end of winter. So right now, we're trying to measure the amount of snowfall over the winter. As you can see, we use this tool to drill down to last year's level. That tells us how much precipitation there has been. Then, we come again in the fall and take a reading from the pole that's sticking out of the snow. How much has the snow settled? How much snow has been added? Or how much has melted away?
Wie viel ist dazu oder wie viel wieder abgeschmolzen ist.
The team has evaluated various scenarios. If global warming continues at the current rate, the scientists expect the alpine glaciers will have melted away entirely by the year 2100. 40% could survive if the temperature increase were limited to a maximum of 1.7 degrees Celsius. Of course, this would have major consequences for the water supply. In the short term, the melting ice would mean more water would be available. But in the long run, the water from the glaciers would be sorely missed.
We're living in the golden age of our water supply. But in the long term, when the glaciers recede and get smaller, they won't be able to supply as much water. And when these water reservoirs disappear, there will be even less water. The second effect the glaciers have is one that happens over the course of years. They serve a storage function. In winter, the glaciers collect snow, which simply lies there and is only released in the summer. That means when the glaciers are no longer there, in the summertime we'll be missing the water that's currently produced by their melting. So basically, in future summers, there will only be water when it rains.
Given the increasing frequency of droughts in Central and especially Southern Europe, having to rely mainly on rain each summer could be extremely problematic. One countermeasure could be to collect the melted glacier water in man-made reservoirs, thereby artificially replicating the glacier's storage function.
Was wichtig ist in dieser Diskussion scheint mir auch, dass
For me, an important part of this discussion is this technocratic approach, that people want to tackle the problem with technology. But when it comes to landscapes like these, I think we need to ask ourselves the question, doesn't nature have a value in and of itself? Can't we just leave it the way it is, because it's beautiful? Do we really have to build something else in these areas? And these aren't questions that science can provide yes or no answers to. Rather, it's a decision that society needs to make, so we should at least consider exactly what it is we want to do.
Ja, man sollte zumindest darüber nachgedacht haben, was man genau machen will.
The analysis of the measurement data shows last winter, this area received more snowfall than in any winter in the last 20 years. That's good news, but not a turning point. The meltwater from the Aletsch and Rhone glaciers converge in the mighty Rhone River. What happens when streams which are fed by small snowfields dry up can already be seen in several mountain regions of Switzerland. In hot summers, emergency water supplies must be delivered by helicopter. Agriculture, industry, and some 10 million people rely on the water from the Rhone. Montreux, Lausanne, and Geneva all border on Lake Geneva, one of the largest freshwater reserves in Western Europe. But for how much longer? Not only are the glaciers shrinking, their precious meltwater is flowing more or less straight into the sea since the Rhone was transformed into a veritable water superhighway for industry and transport. Gone are the floodplains, which would allow water to seep in and fill up aquifers along the river or capture floodwaters caused by heavy rainfall. One exception can be found near the medieval town of Avignon, at the Île de la Barthelas, one of the largest river islands in Europe. Its floodplain forest not only serves as a refuge for animals and plants, but also takes in floodwaters too, allowing the Rhône to spread well beyond its banks. It's an effective means of flood protection, just outside the gates of Avignon. A river that has room to spread out offers yet another decisive advantage, says Gilles Blanc, who's been fighting for 20 years to restore this riverscape to its natural state.
If we give a river like the Rhône enough space and don't take measures to combat flooding, the groundwater will replenish and clean itself. But if we have a canalized, closed-in river, the water rushes through to the sea and can't seep into the ground. If we create a few open spaces for rivers where they can overflow their banks a bit when there's flooding, the aquifers are refilled automatically. It's fantastic and free of charge.
But it's difficult to reactivate these natural cycles, as there are competing interests to consider. In the Camargue region, locks, irrigation canals for rice fields, and its famous saltwater lagoons, the étangs, have forced the river into man-made channels and disrupted the river delta's natural course. Estuaries like the Rhônes play a special role in the water cycle. They are where freshwater and saltwater meet, striking a delicate balance.
Flussdeltas, gerade von großen Flüssen, sind ein Hotspot.
River deltas, especially those of large rivers, are a hotspot of climate change. The effects of rising sea levels are especially noticeable.
Dadurch, dass der Meeresspiegel ansteigt,
for example, when there's a storm surge, the saltwater from the sea will come significantly further inland when the sea level is high than it would if the sea level were lower.
Mit einem niedrigeren Meeresspiegel der Fall wäre.
And, since it's been channelized, the Rhône no longer flushes enough sediment into the delta, leaving little to stop surges from the rising sea. Models created by the European Space Agency from satellite data show that the Camargue could be completely underwater in 100 years. Even now, the intruding saltwater poses a danger not only to coastal ecosystems, but to residential areas as well.
Der Zugang zu Trinkwasser und sichere...
Already today, access to drinking water and a safe, reliable drinking water supply is a defining feature of whether an area can be economically successful.
erfolgreiche Zone sein kann.
In the German state of Lower Saxony, 86% of the state's drinking water comes from groundwater. That's above the German average. Lower Saxony has 750 kilometers of coastline on the North Sea. The rising seawater can be held back with dikes above ground. But what does the situation look like deep underground?
On the coast, we clearly have seawater salinization, or saltwater intrusion. That's the case in Lower Saxony and in many other coastal areas. The deeper down you go, the higher the salinity in the groundwater.
The team from the State Office for Mining, Energy and Geology in Hanover is trying to find out where saltwater is located in the ground.
To the west, so probably will end somewhere.
More precisely, it's about finding the boundary between saltwater and freshwater underground. To detect this, the team works with high-tech equipment. The main component is a huge antenna, a wire frame 20 meters in diameter, which can both send and receive electromagnetic waves. The technology was developed at Aarhus University in Denmark and has been in use worldwide since 2005, from the deserts of Australia to the ice of the Arctic. A helicopter flies the measuring antenna about 30 meters above the surface of the terrain. Electromagnetic fields deliver information from depths down to 300 meters.
Basically, you get an image of the distribution of specific electrical conductivity underground. For example, since clay has a very high electrical conductivity, it's a good conductor. Gravel and sand have significantly lower conductivity. So there's the information on the composition of the aquifer, the subsoil, and on the dissolved salts in the groundwater, which also affect conductivity. That means the more dissolved salt, the more saline the groundwater is, the more conductive it is.
The end result is a detailed picture of the salt content in groundwater. The blue areas near the coast indicate there is salt water just a few meters below the surface. In the green area, there's fresh water at a depth of 100 meters. This is where drinking water can be extracted, just like in the red-colored areas, where fresh water can be found in layers that extend even further underground. The data also offers some unexpected insights.
We've found floating layers of salt water. That's basically a subject unto itself. On top you've got salt water. Then comes a binding layer of clay where the salt water's floated up. Then below the clay there's fresh water, something completely unknown before.
Those saltwater layers are probably the remnants of long ago floods, ones that occurred before people pushed the sea back with dikes. Finding the exact locations of freshwater and saltwater in the subsoil is fundamental for local water suppliers. But saltwater deposits weren't the only unexpected discovery here.
The coastal area is quite interesting. You can easily recognize freshwater outlets under the mudflats. At low tide, freshwater flows out really far into the mudflats. And we could actually show that with this data. So these are the interesting highlights we've stumbled upon.
Finding previously unknown deposits of freshwater is also the goal of this research expedition. In the summer of 2020, the German research vessel Sonne, the German word for sun, set sail for the Mediterranean. Besides the crew, there were 28 scientists on board, along with tons of equipment to study the seabed and what lies beneath it. The ship is bound for Malta. Off the coast of the island country in the Mediterranean, researchers from the Geomar Center in Kiel and their Maltese colleagues plan to use their technology to collect as much data as possible. They're investigating a global phenomenon which could help coastal regions that suffer from a lack of fresh water.
Even in ancient times, people knew there had to be groundwater somewhere in the seabed because they knew there were freshwater springs. And some of these springs were so powerful that the water came right up to the surface. In the Mediterranean, for instance, or in Arabia, the ships could supply themselves with water from these pockets of fresh water on the sea surface. Alexander von Humboldt did the same thing off Cuba, for example.
Marion Jegen is a scientist at Geomar, the Helmholtz Center for Ocean Research in Kiel. The geophysicist heads a team that specializes in electromagnetic measuring techniques. In contrast to the helicopter antenna used in Lower Saxony, the main component here is a device for underwater use, nicknamed the Pig, because one of its forerunners was originally painted pink. Its highly complex electronics were developed and built here at the Institute. The Pig sends electromagnetic waves deep underground. The signals change according to the conductivity of the ground. These changes can be measured and used to infer the existence of possible freshwater deposits in the seabed. By the end of the expedition, the robust device will have covered 50 kilometers of the ocean floor in total. However, collecting electromagnetic measurements with the pig is just one part of the scientists' work. They conduct a variety of technically demanding experiments on board. By taking water samples at various depths, for example, they can determine the salinity of the water. The experiments go on around the clock, with the teams working in shifts. Seismic devices provide an overview of the seabed's geological structure. Acoustic signals are sent downwards, and their echo lets the researchers draw conclusions about the composition of the sediment and rock there. Sediment cores help to complete the picture, as well as to verify and adjust earlier models. There's a lot of hope riding on these sediment cores, since they could provide direct proof of freshwater sources. Malta's seabed proves difficult to work with, since the seafloor is extremely hard. Just 14 samples of sediment core make it safely on board. The cores are then carefully prepared. Only when they're back in Kiel will the team be able to test the sediment for possible traces of freshwater. Then comes the most delicate part of the mission. The pig is prepared for the electromagnetic measurement. The entire apparatus, consisting of a transmitter and a receiver, hangs on a cable that's almost a kilometer long.
We're not looking for groundwater in just one place. We want to scan the entire seabed for groundwater deposits. What we do is follow various profiles. And then we bring the entire device, that is, first the receiver and then towards the end the pig, which is quite heavy, down to the seabed and then pull it along the sea floor. We can get 2 kilometers of profile per hour.
Pro Stunde gefahren.
The relevance of this research is clear, given the huge amount of offshore freshwater thought to exist around the globe. Its total volume is estimated at 1 million cubic kilometers, twice the amount of water in the Black Sea. The impetus for this expedition came from researchers at the University of Malta, who laid the groundwork for the international collaboration. The small island nation located south of Sicily is extremely dry and one of the most densely populated regions in the world. Its area of 316 square kilometers accommodates about 500,000 residents and some 2 million tourists each year. Like many coastal countries, including Israel and the Gulf states, or the U.S. state of California, Malta cannot meet its freshwater needs from aquifers alone. These saturated rock layers don't release enough groundwater to supply the demand from tourism, industry, and agriculture.
In Malta, we don't have any natural resources like lakes and rivers, so we have to revert to the underground natural water and the sea around us. The natural water is restricted to the size of the island, so we had to go elsewhere. And we chose reverse osmosis about 40 years ago as a technology, and it worked. And our plants are still running very efficiently. We have evolved and improved the technology, and we are producing 60% of the water required by the Maltese population from our 3 reverse osmosis plants.
Reverse osmosis functions according to a simple yet ingenious mechanical principle. Seawater is forced through a special membrane under great pressure, filtering out salt and other minerals in the process. These minerals must be reintroduced afterwards to make the water fit for human consumption. Close to 15,000 desalination plants are in use worldwide. People count on this technology in coastal areas where drinking water is scarce. But reverse osmosis consumes a lot of energy. and it leaves behind a concentrated and partly contaminated brine that's usually just channeled back into the sea, although researchers are looking for better ways to dispose of it. Malta has placed its 3 plants strategically around the island.
The main threat is obviously the sea that you can see behind me, because that is the source of the water. So if maybe there is a potential oil spill, it is a threat. But we have catered for that by not taking water directly from the sea, but we are taking water from boreholes. So that makes our life more easy, because oil would remain near the surface while we are taking water from many meters below the surface. So that is a security for us. But if in a major oil spill, we do have a contingency plan to transfer water from one reservoir to the other until the situation is cleared.
Desalinating seawater is Malta's life insurance. The current plants have been designed so they'll still be able to meet the island's demand for drinking water 20 years from now, provided energy costs remain affordable. Producing fresh water through reverse osmosis requires 10 times as much energy as using natural water resources elsewhere, which clearly affects the price. In the future, scientists will need to find more energy-efficient ways of powering these plants and treating their waste products. But the question of how to ensure a sufficient water supply isn't new. Ever since people first settled on this strategically important island, it's been clear that survival here depends on finding a technical solution to the water supply problem. Keith Buhajar, an archaeologist at the University of Malta, is a specialist on ancient and medieval water management. As part of an international team, he surveyed all the island's known ancient cisterns.
What happened was that the area is completely reliant on rainfall. So in order to actually capture all the rainwater that is necessary for an activity to happen, you had this massive cistern being excavated into the landscape. And the cistern is remarkable simply because of the fact that it dates back to roughly around the 4th century BC, probably slightly earlier, to a period in time when Malta was actually under the Phoenician Punic influence.
Around 3,000 years ago, seafaring people came from what is now Lebanon to Malta, bringing with them their invaluable knowledge about water. Could these ancient systems serve as models to solve today's problems?
It's more important to actually harvest every drop of water, drop of rainwater that is available, even today, especially with the prospect and context of climate change. So it is a lesson, I think, that we need to learn, that any void, any subterranean void that was intended as being a cistern has to actually be made functional once again in order to actually harvest rainwater.
The south of Malta doesn't have aquifers, but in the north and west, it's a different story. Here in the Middle Ages, a new technique came to Malta via Persia and Sicily. Medieval builders dug tunnels at the level of the aquifers to tap into these natural water reservoirs. Keith Buhajar is interested in the range of Malta's historical hydraulic structures. From prehistoric water holes to the cisterns of the Roman Phoenician period to the subterranean canals of the Middle Ages. He's already explored more than 80 of them.
Okay, so you've got blue clay, which is an impermeable rock layer. Water is gathering above to form an aquifer. And digging a tunnel, such as this, directly above the blue clay, would mean that you're intercepting a perennial water supply. So this system of water galleries feeding the fields that lie below us was providing that agricultural territory with a perennial water supply. So instead of having 2 crops per year, this territory, because of these water galleries, can provide the continued cultivation of these crops well into the summer months. Okay, so you can get 3 crops per year.
3 harvests instead of 2. These water galleries have a function that could prove decisive, especially in times of climate change and the resulting weather disturbances. The tool marks left by the medieval craftsmen can still be seen today. Most of these tunnels are no longer in use, but feasibly could be put into operation again.
So the big plus of having these systems was the fact that even though you can get a period of 3 to 6 years without any reasonable rainfall, these water systems continued to function. They were enabling cultivation to actually take on. So I believe that there's much scope for better research to take place in the future in order to have such systems which are actually enabling Malta in the future to buffer against periods of extended drought.
When these tunnels were carved into the hillsides in the late Middle Ages, fewer than 20,000 people lived on Malta. Today, there are 500,000 residents, and that population density has consequences.
Die extreme Versiegelung von Böden, die wir zurzeit haben,
the extreme sealing of the soil that we have now means that when heavy rains occur, it immediately leads to dramatic flooding, which wouldn't be the case if we had more open terrain, where the water could trickle away. It's important that we adapt to have more green spaces and less sealed soil everywhere.
Und weniger versiegelte Böden überall.
Incan and pre-Incan civilizations in South America already knew how to make use of different kinds of subsoil to ensure their water supply. This knowledge had been all but forgotten, but now people are taking a renewed interest in the wealth of wisdom possessed by these indigenous peoples. About 10 million people live in the Peruvian capital. After Cairo, Lima is the world's second largest desert city. And Lima is almost entirely dependent on its rivers and reservoirs being replenished by water from glaciers and heavy rainfall during the wet season. Here, the dry season lasts between 7 and 9 months. And due to climate change, dry spells are lasting longer and becoming more severe. It's thanks to what's known as gray infrastructure, dams, canals, and reservoirs made from concrete, that Lima manages to overcome its arid climate. But people are now reactivating a technique that the Inca's predecessors installed in the mountains over the city some 1,400 years ago. Narrow channels made from solid rock are used to divert water from the natural stream beds in the mountains. The principle behind these amunas is simple, yet ingenious.
Amunas are a pre-Hispanic infrastructure designed to take in excess water, no matter if it comes from a gorge or a river. After rainfall in high-altitude regions, the water is specifically redirected to previously selected areas, ones where the rock has fissures or fractures, or the soil is highly permeable.
During the rainy season, water no longer rushes down into the valleys unimpeded and when there forms raging rivers that flow into the sea. Instead, the water is redirected and slowly seeps into the ground over a large area. Already over 1,400 years ago, the original designers of these canals demonstrated profound knowledge about the geology of their region. The Amunas feed very specific water-bearing layers of rock underground, which then, often kilometers away, emerge as springs. The water can take weeks or even months to make its way through the different subsoils. All the while, this precious resource is being stored for long periods, well into the dry season. A research group from Imperial College London set out to better understand how the system engineered by indigenous peoples works. In their amateur video material, you can see the huge amounts of water rushing down the hillside during the rainy season. In a large-scale field trial, they pour degradable dye into the canals. In order to track where the water diverted here later re-emerges as groundwater in springs. The incredible result? Up to 8 months later, the water can still be found exactly where it was predicted to go, sometimes to water sources quite far away. Now, with the support of local environmental initiatives, residents of a few villages in the Andes are working to expand the Amunas.
I'm pleased to finally restore this great thing our ancestors created.
The knowledge of pre-Incan cultures is now receiving worldwide recognition after the research conducted by the team at Imperial College London.
The water will help us to get better products, produce better harvests, and be able to sell them better too, so we ultimately earn a bit more profit.
Meanwhile, there are thoughts of applying the principle behind the Amunas on a larger scale. For instance, a timely implementation of this technology could increase the water supply available to the metropolis of Lima by more than 1/3 during the dry season. On board the research vessel Zona, scientists from the Helmholtz Center for Ocean Research, GeoMar, complete their measurements. After almost 7 weeks, the vessel returns to its home port of Emden in October 2020. That's when the evaluation of the data and samples begins. Some 30,000 sediment cores from around the world are stored in Kiel. It's a valuable archive of the underground and of our global climate. Only half of every core sample is used for further research. The other half is preserved to serve as a reference for future generations. Geophysicist Christian Berndt, who heads GeoMar's Marine Geodynamics Research Unit, was in charge of the expedition to Malta. The precise analysis of the sediment samples isn't yet complete, but the team has made some preliminary findings.
What we didn't find during our expedition were places where the groundwater leaks into the sea. Looking around the globe, there are actually places where there are small sources of fresh water on the sea floor. But we didn't find anything like that. And we looked very carefully, using many different methods. If they existed, it's highly likely we would have found them. So the groundwater in Malta really is trapped underground and isn't flowing out.
But just because no fresh water is seeping out doesn't mean that there isn't any there. It could be enclosed in water pockets.
Right now, we don't know enough about these groundwater deposits on the seafloor. With our methods, we're just starting to be able to find them and prove they exist at all. It could be that these bodies of groundwater are no longer connected to the land. That means they'd at some point become salinated by the salt water around them. Or it could be that these groundwater bodies are still connected to the land and are being refilled from there. We still don't understand this whole dynamic, and that's a major focus of our project, to try to understand this dynamic and see if, eventually, it could be used sustainably.
Sustainability is the core issue for the future of our water supply. Protecting and preserving drinking water isn't simply an ecological challenge. There's yet another aspect that concerns Friederike Otto.
A lack of drinking water and reduced access to fresh water is one of the major effects climate change has on our social system. For instance, in Germany, there's a lot of discussion about drought and the effect on forestry. But there's no discussion about how this may also have consequences for the price of drinking water in certain cities or areas, which would thus have an influence on people's cost of living.
Darüber wird gar nicht geredet. Und das ist eben nicht nur,
the price of climate change is not only being paid by poor people in East Africa, but by poor people in Europe too.
Auch von armen Menschen in Europa.
Research that promotes understanding and helps us draw the right conclusions is critical.
All is not lost. That goes for the glaciers in the Alps too. It all depends on what we do now.
We can all take action. Water conservation can be practiced on many levels.
The solution must be interdisciplinary, but that also means we must really engage with other disciplines, work very closely with them to see how we can fit all the pieces of the puzzle together. And of course, that's also exciting for us as scientists.
Preventing our water sources from drying up is a challenge for the entire global community.